Hi, my name is Martin Lower. I'm the CEO and co-founder of Sixonia Tech. In the next few minutes, I will explain you a little bit what distinguishes our E-Graphenes from other graphenes that you can find on the market. So, as you probably well know, graphene is a wonderful material that has a lot of beautiful properties combined in a single material. So it's very strong mechanically, it's very conductive, and it's not permeable to any gases, for example. So when it was discovered and awarded with a Nobel Prize, many people were basically dreaming that we could fly around in graphene planes or aircraft or drive around in graphene cars in the next few years, but this unfortunately hasn't happened. And the reason for that is basically that as a new material, graphene is facing quite some challenges, just like any other new material. So one of them, and probably the most important, is that you can usually not find a graphene that is both easy processable and of good quality. So I will explain a little bit more why that is, but this in turn leads to several problems. For example, in applications where you want to use graphene as an additive, you might add graphene, but you will not get the benefits you expect because, yeah, the quality is just not good enough. Or you might add graphene and you might find that it's just not really processable in your matrix material, for example. And this, of course, leads to problems where the cost versus added value cannot be met in a satisfactory way. So in 2020, there was basically a market study done, or a big survey with more than 800 people working with graphene or interested in working with graphene. And what that showed is basically most of these people are really interested in functionalized graphene. Probably this is for the exact same reason that I've mentioned before. So with functionalized graphene, you can bridge this gap between the processability and the quality of the material. So if you look at the material characteristics that are typically needed, people both want dispersibility, which means processability into any kind of solvent or matrix material, but they also want electrical conductivity, which is always an indicator of a high quality material in terms of graphene. So if you look at graphene technologies that are currently used to produce graphene, you can basically distinguish between bottom-up technologies and top-down technologies. So bottom-up is basically where you start from small molecules like methane or CO2 to build graphene basically from scratch. This is a very interesting technology that can be used to produce very thin layers on different substrates and produce really large area monolayer graphene that is interesting for applications in electronics, for example. On the other hand, you have materials that are basically produced from graphite. So you take graphite and you just make it thinner and thinner and thinner, or you take graphite and you oxidize it to produce a material called graphene oxide. Basically, what I want to say is that there are several drawbacks for each of these methods. Obviously, with a bottom-up approach like CVD graphene, you cannot easily produce tons of material. So if you're looking for composites, that might definitely not be the right way to look. And in the other cases, basically, you are somehow changing either the properties of the material tremendously, like in the case of graphene oxide. Graphene oxide itself is nicely processable, but it doesn't have any conductivity anymore because of the oxidation that you introduce. And in the other case, you have a purely mechanical process, which in turn leads to a material that behaves basically the same like graphite. And I will explain it a little bit more. So nevertheless, all these different approaches have their merits, and they produce materials that might be good for a specific application. So I don't want to badmouth any kind of these production techniques, but you really have to be aware that there are a lot of different graphenes out there, and it might not be obvious in the beginning which graphene is the best for your specific application. So it's always interesting to look at that and keep it in mind. So one example can be a problem with the mechanically exfoliated graphene, for example, is that if you look at the graphite in a perfect world, you apply these shear forces much like they did it in the original Nobel Prize experiments with the Scotch tape, and these shear forces are aligning nice and parallel to the graphite sheets. But obviously, in a real world, these kind of shear forces, if you apply them using sonicator or a shear mixer, they will act in random directions. So they do not only work with like to exfoliate the graphene, but also the exfoliated material of the graphene will be like cut in the middle, for example. So the particles you get, the thinner they are, also the smaller the lateral size will get, which basically doesn't have to be a problem yet. But the next thing is that will happen in a dispersion if you have it like this, is that if you have a material that is basically just mechanically exfoliated, and that means you don't really change the properties chemically of the material that you are producing. So the material that you are exfoliating basically behaves the same like the original graphene layer that was incorporated in the graphite, which means it will have the tendency to stick back together and form graphite again. So the only way to overcome this is basically by adding surface active molecules that we also call surfactants, or in easy words, a soap. And this prevents the material from sticking back together. Problem with adding surfactants basically is, on the one hand, if you have a material that is already small in particle size, and it's not like in a metal, so if you have a conductive ink, for example, using graphene, it will not behave like you would expect it from a metal ink, for example. So if you have a metal particle, you heat it, basically metal particles can fuse together, and that's not something that will happen with graphene. So the limiting factor in any kind of conductive applications will always be the contact resistance between two graphene sheets. And obviously the influence of the contact resistance will be much bigger if you have smaller particle size, because it just increases the number of contacts. And if you have a surfactants, obviously it increases the distance between two graphite sheets, and that always increases also the resistivity. And the other problem is that if you have for example, you're looking into composites and you want to use graphene as an additive to, basically to increase the mechanical strength, for example, you need a certain size to have an interaction of your matrix material with your filler material. Otherwise, you're just creating defects in your bulk material. And if the particle size is very small, then this is really difficult to achieve unless you have a covalent bond between the graphene filler and your matrix material. So in case of having a surfactant and small particle size, this is really something which is rather difficult to achieve good mechanical improvements with such kind of materials. So what we have basically is, we have on the one hand, we have graphene oxide as a large scale production method that you can find like really performed on the ton scale, and it's a scalable method, and it's good for various things. So graphene oxide is really nice material to play with and to functionalize, for example. So it can be easily modified due to the plethora of functional groups that are already present. But the fundamental challenge is that the process is quite environmentally dangerous, I would say. So you produce a lot of wastewater and heavy metal residues that you need to take care of. And eventually the material that you get is over-oxidized. So you produce so much defects that you get a processable material, but it's not conductive anymore. So this can be a problem for your application. And in the case of the mechanical exfoliation, basically I've already pointed it out, you always have the discrepancy of the flakes are getting thinner and thinner, and you really get a few layer material that has this typical graphene-like properties. The lateral size will always be rather small, and on the other hand, you have this very high purity, but due to this high purity, you will always need additives to process it. So how can this be solved, basically? And this is basically what our mission is at Sixonia. So we have a material that's called electrochemical exfoliation, or electrochemically exfoliated graphene. And what happens here is basically we take graphite, we apply a voltage inside an electrolyte. The ions from the electrolyte are driving in between the graphene layers, just like they do in a battery, for example. And then also water from the electrolyte is entering into the network, and due to the electrical potential that we apply, the water is split. We have gas bubbles creating that are pushing the graphene layers apart. So this is basically well known in literature. So the unique thing that we are doing here at Sixonia is basically that we modify this electrolyte and we add different additives to the electrolyte. And with these additives, we can introduce functional groups to the surface of graphene, which in turn allow us to have a material that is easily processable without having too many defects to really destroy properties like conductivity and things like this. And so what we really can achieve is basically high quality material that are easily processable. For example, we can process our graphenes in water and disperse them in water without the need for surfactants. The functional groups can basically be tailorable to the application and to the matrix system that you have and that you need. And yeah, the whole process is quite green and scalable. So if you look at a general spec sheet of our material, we can really have lateral sizes in the micron range, which is comparably large, especially compared to the liquid phase exfoliant materials, while typically our materials that are in dispersion are really few layer graphenes, so typically 5 layers and less. And the functional groups could be tailored depending on your application. Whereas the conductivity of this material is still rather high, so in the range of 100,000 Siemens per centimeter for a bulk film. For graphene is a very good material and a very good property, unless you're talking, for example, about CVD graphene, which of course will outperform that, but is not available on kilogram or ton scale easily. We are currently setting up our first pilot line with basically a capacity of 1 kilogram producing graphene per day. So this will be this is happening right now and will be finished this year. And eventually, if we are talking about even larger scale production, we are also very confident that we can reach prices that are way below 100 euros per kg. So that is also not actually more expensive than the other graphene methods that you probably have heard of before. So with that, I would like to close, and if you are interested, please get in touch and we will figure out how we can unlock the potential of graphene for your specific application. So thank you very much.